and 40 remaining 60% will be the moderate level question. So difficulty 20% question will be. That's right.
So which part is most important for this exam?
Week 1 to week 4.
No, that's the whole syllabus, I guess.
Yeah. So everything is important in that. That's what I mean.
Okay, so means among them, if I specialize, means if I want to focus on some part, then sir.
Get comfortable with the RREF form, how to obtain them. That will be useful.
Okay,
Basically, finding out basis, finding out dimension, finding out rank, or in all of these, finding out whether given set of vectors are independent or not. For everything, you need to use RREF and Gaussian equation. So just get into.
okay, sir.
Excuse me, sir.
Yeah.
Sir, I have one doubt. Can I ask now? Just a small conceptual doubt.
Yeah, please go ahead.
Sir, I have a doubt like if some vectors are given, like three vectors are given, and the vector set is given, and then we will arrange it as the columns of a matrix. So, sir, to find the basis, like if all are forming, like we are getting all as the pivot columns, like there is no independent variable, all are dependent variables, then what will be how to compute the basis for that matrix?
So then all of your vectors, all of your columns are form the basis of the column space.
Sir, so like if the vectors are like 2, 1, 1 and 3, 1, 2, something like that, so the basis
Yeah.
will be 2, 1, 2 and 3, 1, 2 like that.
Yes.
Okay, okay. Thank you so much, sir.
Okay. So shall you have a down in AQ 4.4, Q7? Let's see whether I cover that in this, because I've taken some questions from the activity questions. So I think I might cover. Yeah, I'm covering that. So I will cover that question. All right, so let's start with today's discussion. So today we are going to revise week 3 and week 4. Yesterday's discussion was for week 1 and week 2. So main point of discussion of today's meeting is for quiz 1. So we are doing revision session for quiz 1, week 3 and week. So so week 3 starts with the definition of vector spaces. So here is a quick recall to that. A vector space over R has two operations, addition and scalar multiplication, where it needs to be closed under both of the operations. What does it mean? That if you add two vectors, then their sum also should lie inside V. All right. And scalar multiplication means if you multiply a scalar to a vector, then their scalar multiplication also lies in the space. And then these two operations need to satisfy these 8 properties. Okay. So first property is commutativity of this. Second is associativity of addition. Third is the existence of additive identity. Fourth is the inverse of additive inverse. Third one, fifth one, and sixth one are for the scalar multiplication. That scalar is multiplication is associative, and multiplying one to a vector gives you the vector. Sixth, seventh, and eighth property is the distributive properties. All right. So keeping this property in mind, let's solve this question. Can everyone see this question? Now is it better?
Yes, sir.
Okay. All right. So So I will give you some time to think about this question and then you can answer me. So basically you need to tell me which of the, so there are 3 vector spaces. In particular, there are 3 sets with addition and multiplication defined on each of them. You need to tell me which one of subset, which one of the subset forms a vector space, or which one of the set forms a vector space. You can write your answer in chat box. You don't need to say it out loud, so that others can also. So let's name them A, B, C. Yes, Neil, do you have anything to ask? Okay, some of you are saying none of them. And okay. Oh, none of them for most of. Okay. Okay, so let's see one by one. So clearly, first one is not the vector space because of this addition defined in this way. It does not have the identity matrix, because if you add 2 numbers, if you are going to add right, so if you add 2 vectors, you are getting this. So what is the 0 identity? In this case, there is no 0 identity.
Excuse me, sir.
Yes.
Sir, can you please tell what is going in the class, because I got late and sorry, sir.
This is going on in class. I'm discussing this question. You can answer which of the vector. You can read this question, right? This question is visible to you. So we are just discussing this question. All right. Okay. Good. So most of you have already answered that none of them forms a vector space.
Sir, could you please explain why option B does not form vector space?
Yeah. Can anyone tell that?
So please explain option A also, sir.
Okay. So does anyone want to explain why option A is not a vector space?
Option A is not vector space because according to definition of addition, the third coordinate is always 1, while it is not mentioned in the original given set. It can be 1 or anything also, but according to addition, it will be fixed 1.
So it does not solve the fourth property, v plus v dash is equal to 0.
Yes. Basically, the existence of the additive inverse. Right? So but what is the additive inverse in this? What is the additive identity in this case?
The commutative also it won't follow.
Commutativity, right? Good. Commutativity is the actual problem. Sorry, commutativity. Okay. So can everyone see that? So what is commutativity? Addition. So order matters. So commutativity says that order does not matter, but in this case, you can see the order matters. So if you add x2, y2, z2 first with x1, y1, z1, what you are end up with? x1, x2. First coordinate, no problem. Second coordinate will be y2 plus 1. Third coordinate will be z1 plus 1, which is not equal to this. So it is not commutative. Good. What about the second B case? Which property is not satisfied?
Sir, again, it won't be commutative.
Right. It is not counted.
Sir, and the sir identity that sorry additive identity is not unique in B.
Additive identity is not unique. Okay. So tell me two additive identities. One is, yes, there are infinitely many additive identities.
Yes.
That is true. But also, you can also use the argument that it is not commutative. That is also fine. You don't need to go to the third property. You can just start with the very first one. This one. Right. Okay. So second is also not commutative, not additive, commutative. Okay. What about the third case? So third one is commutative also. It is associative also. What is the additive identity in third? 0, 0, 0. Right. What is the inverse in third case?
x1 is equal minus x2.
Yes. For you have a vector like this, and then what will be its additive inverse? A, B, C, such that you get 0, 0, 0. So it should be just x2 minus x, but there is no condition on B and C. All right. So now let's go to the additive inverse.
Sir, there are infinite number of additive identities.
Yes, but there has to be unique one. So that's
yes,
the problem. There will be infinitely many additive values, but there has to be infinite. There has to be one. So this is also not and vector space. So problem is infinitely many additive inverses. Even additive identities are also any 0, comma.
So at this infinitely many additive inverse, that point I could not get.
Yeah. So there can be, what is additive identity? Can you recall? The one who asked.
Additive identity is that the vector, if we add to the original vector, it will return the original vector.
Yes. Right. So let's do that. So you have a vector x, y, z, and you want to find out an additive identity a with c such that if you add them, you get back the original vector. But the summation is defined like this, that you can never get back the original vector. So it will always be x plus a. But this x plus a has to be equal to a. So this forces that a has to be what? A has to be minus of a has to be 0. But y and z need not to be 0. Right? Y and z need not to be 0. They can be any other thing. So there is no additive identity. There does not exist any identity. There are not infinitely many, but there does not exist any identity. Okay.
Yes.
Sir, I have one small question to ask. Sir, in these 8 properties, why don't we talk about commutative multiplication? Only addition commutative we discuss, but is it like inbuilt somewhere, or we are just not bothered about it?
Commutative?
Multiplication to be commutative, we do not discuss it here. Is it not required?
Multiplication to be commutative. So what do you mean by that? AB B is equal to
BA.
BAB.
Yeah, I mean multiplication of two vectors and then the order does not matter.
There is no multiplication of two vectors. We have
Okay.
not defined multiplication of two vectors.
Yes, yes. Oh, sorry. Yes.
There is
sir,
a scalar multiplication.
Yes, yes. Correct, sir. Thank you, sir.
All right. So there is no additive item. All right. So this is not a vector space also. All right. So none of them are the vector spaces. Good. So now let's recall what is a linear combination of vectors. So suppose you have a vector space and you have n vectors in your vector space, set of n vectors in your vector space. Linear combination of these vector spaces with coefficients a1 to an is a vector of this type. Okay. You multiply the scalars with a vector and then you add them. That's called the linear combination. And further, you say a vector in vector space is a linear combination of a given set of vectors given to Vn. If there exist some scalars, so that you can write V as a linear combination of those n vectors. So this is called the linear combination. So linear combinations help you to define linear dependency, dependent vector, and linear dependent vector. So let us quickly recall what the linear dependent vector is.
Excuse
Suppose
me,
you have
sir.
Yeah.
Sir, while explaining this linear dependency concept, can you explain linear dependent and independent variable too? Because I get confused in all these four. These are like similar dependency factor.
There is nothing to be confused about. Whenever you say linear dependent, there is a linear dependent vectors. There is a vector involved. Right? When you say linear dependent variable, so there is a variable involved. So there is nothing to be confused about. Okay, and there is no linear dependent variable. Variable is just dependent variable or independent variable. There is no linearity over here. Okay. Yeah, I will talk about those things at the later half of session.
Okay, sir.
Okay. Linear dependence is, you say set of vectors are linearly dependent if there exist scalars a1 to an. Not all of them are zero, such that their linear combination with these scalars is equal to zero. This gives you the zero value. All right. And when you say when there is a unique solution, that means all of these AIs are zero, then such a linear combination, such vectors are called a linearly independent. Right? So if your set of vectors are not dependent, then they are linearly independent. So this is also one of the observations that we saw in the sessions, the live session, that more than n vectors in Rn are always linearly dependent. And to check linear independency of n vectors in Rn, right? To check the independency of n vectors in Rn, we can use the determinant. Okay, how you can write each of the vector as column. We can write each of the vector as column, and then you can take the determinant of this. The determinant of this, if it is non-zero, if the determinant of this is non-zero, then the set of vectors are independent. All right. So this you have already seen. Now let's do some exercises. Okay. So this question says each column of n cross n matrix A can be thought of as vector in Rn. If set S consists of all column vectors of A, then which of the following is are true? All right. A is always linearly independent. S is linearly independent if determinant is non-zero. It is independent if determinant is 0. If determinant is 1, then it is
Option 2 and option 4.
Option 2 and option 4.
Okay. So first option is incorrect because there can be a matrix with dependent columns. So this is not always true. Option B is correct. because that's what I just said. You can write vectors as column and then you can take the determinant. If the determinant is non-zero, then they are independent. And that's what it says particularly. Similarly, if the determinant is 0, then they are dependent, not independent. So this is wrong. Option D is determinant is 1. That means it is non-zero. So the columns are independent. That means set S is linearly independent. Okay, good. What about this question? So you have given a set of vectors. Set of vectors are given. Then choose the set of correct option. Okay. So the singleton is linearly dependent. A singleton set is linearly dependent.
False.
No, sir, option 1 wrong.
Okay. Okay. A singleton is always linearly independent. Okay. So this is false. Okay. Yeah. Now second option. Now second option says if S is a spanning set of vectors P, then S union V must be spanning set of V.
Yes, sir.
Is that correct?
Yes,
Yes,
sir.
correct.
Yes, sir.
Superset.
No. So I have not talked about a spanning set. So I will come to this exercise once I do that. Okay. So till now I have only discussed what linear with order. So let's skip this and then discuss the span of vectors first, and then we will come back to that exercise. Okay. So what is a span of vectors? Suppose you have a vectors set of vectors given, n vectors given in your vector space, and you look at all possible linear combinations. We know that the linear combination is always a vector in V. So you look at the all possible linear combination, that is, and you form a set. You form a subset of V. Okay, that is called the span of those n vectors. Moreover, the span forms a subspace of a vector space. Okay, so what is a subspace? Subspace. So it forms a subspace of a vector space. Now, what is subspace? Subspace is a subset of vector space with addition and multiplication same as the original vector space, and it is closed under the addition and multiplication. Okay, that is the subspace. For example, real lines in R2, real lines passing through origin in R2 forms the subspaces, or planes in R3 that passes through origin forms the subspace of R2, or lines in R3 that passes through origin forms the subspace of R2. All right. So those are subspaces. Now, notice that span of vector spaces also form a subspace of the vector space. All right. Okay. With this definition being clear, now let's go back to the question. Okay. So now, which of them is correct? S is the spanning set of the vector space, then S union V must be spanning set of.
Yes, it should be true.
Yeah.
It is true, right? Because S is the spanning set of vector space. So if you add any more vector, it won't change the fact that S already spans it. It added more information. We have added more information. So it doesn't matter. Okay. The span of empty set is the zero vector space. Is this correct?
True.
Correct.
Yes. No, if there is no, if it is empty set, there is no vector.
It's the zero space, zero vector space. Empty say
What is an empty set?
null set.
5.
5. There is no vector. So if you look at the span of something which is not there, then what will it give you? Give you the empty set. Right?
So
Span of an empty set is zero vector.
Sir, could you please explain option 2 once again? Briefly, option 2.
Yeah, what
Like
is a span? Oh, sorry, what is an empty set?
we have
No,
nothing.
not the empty set option. That if S is a spanning set of vector space V, then S union V. How will it be always spanning? How to understand or what to?
Okay, anyone want to explain that?
Yeah, because if a vector space is already proved as spanning, then whatever vector we can add, we can simply use the coefficient of that as 0 and make the whole vector as spanning.
Whose coefficient will be 0?
The other vector which we are adding, if we take the coefficient to be 0, then it would also act as spanning only.
Zero.
All right.
And if coefficient is not 0, like AV something, if we do the combination.
No, for you have to, for making a
Can you get
span,
can you get a vector which is not in your vector space? You cannot get anything outside of the vector space because all the vectors are sitting inside your vector space. So adding more information won't lead you to a vector which is not in your vector space. You already have a spanning set which spans your whole vector space. So if you add one more vector to that spanning set, it does not change anything because you are already spanning the whole vector space. So
It's
there's
actually spanning set is just the set on which we are applying the span. A set of vectors from the vector space on which we are applying the span. So,
yes,
but
and that span is the vector space, right?
yes, a subspace of the vector space.
No, in this case, it is given that it is the vector. That is the vector space.
No, it is given that S is the spanning set of the vector space V. So, when we apply the span, it will be a subspace of V. If it is equal to V, then it will be basis or
Oh,
something.
okay, right. Okay, I was reading it. Oh, yeah. Okay.
No, I was trying to ask
Yeah.
that means someone said if S is proved to be a
No,
spanning
it
set.
is no. It is a spanning set of vector space V. What does it mean?
It is just the
What do
set
you
of
understand?
vectors we are picking up from the vector space V on which we are applying
Yes.
the span, like the set of all
Yes.
possible
And
linear
what is that
combinations
span?
on that
What
S.
is the span? What is the span?
Span will be a subspace of the vector space V.
What is the span given? So S is the spanning set of the vector space. What does this line mean? It means that spanning set, that if you take the span of the vectors in the spanning set, it gives you vector space V. That is what it says. It
Basically,
says
also
that
it's to
the
put in.
span of S is V. That is what it says. Is it not clear to you?
All possible vectors.
Is there a doubt?
no, it's okay. Sir.
No,
Yeah.
sir.
That means if span is equal to V, then S will be the basis. That is the condition. But here span S should belong to V.
S need not to be basis. Don't get confused. Don't add more terminologies to this. S need not to be a basis. First of all.
Okay.
Yeah. Now what's your doubt? I am not able to.
Doubt is this option only. How did we understand that? Means when we obtain the span, the S union V, how will it be always the spanning set of V? That is only I originally asked.
Okay, you write down the spanning set of S union in your notebook. You are thinking in your head only. You write down that thing. Okay. And then you prove that the span of, so you do this one thing. So you start with, let's say, the span has some VM elements. Okay. And you look at the span of this. So you do this exercise. Okay. In your notebook. The span of this is V. This is given to you. Okay, we know this. All right. Now, what do we want to prove? We want to prove is that the span of V1, Vm, and V is equal to the span of V1 of V. All right. How do we prove that? You take a vector. Which is in this, and then you prove that vector also lies in this. All right.
Okay, understood. Means the spanning set is equal to the vector space that is already given. On the basis of that, we are doing.
Yes, it is all. It is given. Look,
Yes.
read the
Sorry, I
first line.
misinterpreted the option. Sorry. Thank you.
Yeah. All right. Okay, so span of an empty set is the zero vector space.
So this
If
should
it is empty set,
true.
if it is empty set, there is no vector in it. Then we look at the span of it. The span will also be empty set. It won't be the zero vector space.
Sir, I'm
Sir, if you
sorry.
think,
Sorry to
sir, if you
interrupt.
think about,
Yeah.
So, but I think in the video lecture it was mentioned that we take it as a convention. Span
Okay.
of concept is a zero vector space, but
Oh, if we do so, then it is. Let me just quickly check.
sir, if we think of it as a direction also, if the empty set, if there's, if we are given the empty set, then there is no direction to be span, right? Like,
That's what I'm saying.
Yes,
So if there is
because
no empty,
yes, zero vector is also a vector. It can't be an empty set.
yeah, but right, it is assumed to be true. Okay.
like if we think of it in the direction terms to in a graph, so
Yeah, I think so. Yeah, but empty set means there is nothing.
So,
Okay.
but the
So let's.
subspaces, but in case of a subspace, so we have a 0, 0 kind of line which passes through a, supposing we have a subspace, there's a line passes through a zero subspace. So we consider it as a, so then can't we think it like that in that way?
No, what? Okay. So my doubt is more or less on logic base. It's just not. So we can assume with the convention that empty set means there is zero vector. So if you look at the span of that, you will get zero vector space.
Yes, sir.
That is,
Excuse me.
Yeah.
If it is written in a question or any statement that if S is a spanning set of the vector space V, does it mean that span S equal to V by convention or something? That I think I'm making mistake. Like if it is mentioned that here option only that if S is a spanning
Yeah. So what it says? Okay. So what does it say? Spanning set of the vector space.
yes, spanning set of vector space. Yes.
So what does it say? If it was a spanning set of something else. Oh, there were two questions. Well, that's why we just got mixed up. Okay. Okay, so let's. Oh, that's why it must be confusing. Yeah, so this is a different question. It's not related to the one that we were doing. Yeah. So because it is the spanning set of the vector space, that's why yes, it is not a vector. It is not a spanning set of some third subspace. It's a spanning set of the vector space that is given.
Yes, it is spanning set of vector space V, that is understood, but it is spanning set of vector space V. Does it mean that the span of S will be equal to V?
Yes,
Exactly.
that exactly that.
Hello?
Yes. Yeah, that is what it means.
Okay.
If S is now what was the third option? If S is a spanning set of a vector space V, then S minus V must be the spanning set of.
Yeah, false.
For all V in S. Right, not for.
Must be is not correct.
And the T is also wrong.
Sir, what should be the condition for a S to be a spanning set of vector space V?
Last option is correct, sir.
No, it may not be spanning set. That's what. But it is already given to be a spanning set. If you add, then it may not do. That is a wrong answer.
Excuse me, sir. Hello.
Just wait for a second. Neil.
Okay.
Yeah. Yes, Ajit, do you have anything to say?
Yes, so like when there are questions that ask us whether a certain set of vectors is a spanning set of R square or cube or like stuff like that, like do we have to make sure that none of the like axis values become zero when we add it together so that it will be like will be
That is
satisfactory for
basis. That is basis. That is not the spanning set. Don't get confused. The spanning set just means that it spans the whole vector space. That is, any vector, if you take in your vector space, it can be written as linear combination of the vectors coming from the spanning set. That's all. You don't have to check for the linear independence. All right?
Okay, got it.
Yeah, if it is not given to be a basis. Don't get confused with the basis. Yeah, so you were asking what is the condition of spanning set to be a spanning set? I don't understand what is that.
No, means a set S is a spanning set of a vector space V. What should be the condition on S so that S should be a spanning set of vector space V?
What is the definition of spanning set? Can you tell me that?
Spanning set is the set of all possible linear combinations of the vectors in
No,
vector
that is wrong.
space.
That is wrong.
That is span, I told.
Yes. What is a spanning set?
Spanning set is basically the set from the vector space on which we are applying the all possible linear combinations. That is the set on which we are spanning. That simply we say. Yes, the set of the within the vector space on which we are applying the span operation, like trying to find out all possible linear combinations and what it gives.
Yes. So when you say you have a subspace whose spanning set is given, then what does it mean?
Sorry, subspace. What is given?
So you have a vector space.
Yes.
Whose spanning set is given. Then what does this mean?
Spanning set is given means a set within from the vector space itself is given, and we have to do all the possible linear combinations of that.
When this is given, that means that vector space is the span of that space. That's what it means.
Means I am telling this
When you
because
say S is the spanning set of the vector space, So when you say S is the spanning set of vector space, it simply means that the span of this spanning set is equal to the vector space. I don't want to emphasize more on this. I don't know what is not what you are not able to understand. It is simple English. Okay, there is nothing more going on.
No, means at the beginning it was mentioned, and we had also seen earlier that the span we obtain is a subspace of the vector space.
Yes. So is vector space not a subspace of vector space?
Check it from week 4 content, Neil. It will be much more clearer to you. Let us continue.
No, just let me answer this, Neil. I'm answering every query of yours. Just answer this.
Yes.
Is vector space not a subspace of vector space?
Yes. Okay, understood.
So from next time onwards, I want you to think first. Okay, just don't ask me directly and stop me in between. Okay, it really breaks the flow of the session. Okay, I appreciate that you asking question. I really appreciate that. But please also make sure that your question also makes sense, and you keep on asking the repetitive things, and if you keep on repeating the same thing again and again, so it is also like time taking for others also, okay? Because we need to cover a particular session, we need to revise the whole syllabus, right? For quiz. So just try to think first of your own. If you are having trouble, write down the things. Okay, do it on your notebook, and then try to ask. Okay, so one more thing for everyone else, if you have any question if you want to ask, please raise your hand. Okay, so then I will ask each one of you one by one and you can ask your queries when your turn comes out. Okay, so let's come back to the session. Question 9, whichever this is given. So I had not discussed this earlier because it was overlapping with the previous question. Okay, so we have set of vectors given to us. Choose the correct option. We have already seen that the singleton is not the link, is always independent. It's always independent, so it's wrong. If alpha beta are in the set as an alpha beta are distinct, then alpha beta are linearly independent set of vectors. So that means what it says that if you take any two vectors from the set, are they independent? So you can check this condition. Okay, this will be just a check. Okay. All right. I think they are independent. First glance, they look independent.
Because any vector is not a linear combination of others.
Yes, that is true. Now, what about the third option? If you take this particular subset of your spanning set, then are they independent set of vectors?
Yes. Yes.
Yes, they are independent. How you can check they are independent? You can use, because there are 3 vectors in R3, so you can write each of the vector. You can write each of the vector as column of the matrix, and then you can find out the determinant. One way is this. Second way, you can write each of the vector as row in your matrix, and you can apply the row echelon form. If it has, if the rank is full, then it is independent. We have also discussed to find out determinant using that. That's another way. All right. S is linearly independent set of. Is there any question?
If we write this as rows, then also the determinant would be non-zero.
Yes, yes. Right. It doesn't matter because the transpose does not change the determinant. Right. The set S is linearly independent set of vectors.
False.
Right. Why?
So because in R3 vector space there are 5 vectors.
Yes.
So it automatically
So
makes them
anything more than 3 will be independent. Will be dependent. This was alpha beta gamma is linear independent set of vectors for any alpha beta gamma in this, where all of 3 are distinct vectors. Okay, so if you take any 3, then will they be independent?
So it's false.
False. Okay, can you give me some example? Yeah, I think you can take these 3 vectors, first 3 vectors, and then so you can take alpha this, beta to be this, and gamma to be this. Then you can see that gamma is nothing but alpha plus beta by 2, right? By
So
4.
option C also it's clear.
So alpha beta gamma. Okay, if this is an independent set for any this where all 3 vectors are distinct. Okay, sorry, the other way. Okay. So if you find out a set of 3 vectors which are not dependent. All right. Yeah, set of 3 vectors which are not independent. Sorry. Which are independent. Sorry. So yeah, you can take these 3 vectors. These 3 vectors are independent to each other. All right. So it says that not any combination of 3 vectors will be dependent. Right? So this is what. Make sense?
Yes, sir.
Yes, sir.
Yeah. Now for the fourth, last option is alpha beta gamma delta is linearly independent set of vectors.
True.
For any alpha beta gamma.
So false again, number of vectors.
Yes, number of vectors. Good. So this is false. All right. So there are only 2 options correct. Okay, good. So you guys are doing good. Now let's. Yes, Arnav. Arnav, do you have anything to ask?
Yes, sir. Could you just please explain the fourth option of the previous question?
Fourth option. Set of
No,
S is
second last.
linearly
Sorry,
independent
second
vectors.
last. No, second
Second.
last actually. Yeah.
This one.
Yeah.
So it is saying that alpha, beta, gamma, where any alpha, beta, gamma are in this spanning set, are in the subset S, are linearly dependent set of vectors.
Yeah.
Okay. Where all are distinct vectors. So you need to come up with, in order to prove that it is false, you need to come up with three vectors which are independent. All right. So that's what I did. If you take last three vectors, then they are independent.
Okay. Okay. Got it. Okay.
Or you can just take these three vectors, which were there in the option C, third option. You can take these three vectors, so they are independent. So not any combination of three vectors is.
So basically it's asking that whether if we take three vectors, then all of them are linearly dependent. So it's stating that, right? So we have to prove it wrong. So
yes.
Okay.
Yes, Moon.
Sir, so how the last option is false? Because like area 4 vectors, so we are saying this is linear independent. It means span is 3. But how we know?
Yeah, because four vectors are there in R3, so they will always be.
But how this is R3?
How this is R3? Look at the vectors. It is 1, 1, 1. They are in R3.
Okay.
So if you take any span of these vectors, they will be a subspace of R3. It cannot go beyond R3.
So, sir, I have a doubt. If in the second last option, if it was written linearly independent, would it still be correct?
Then also it is wrong. Then also is wrong.
Because any three random vectors are not coming as independent, yeah?
Yes.
Okay.
For that, look, you can take this first three vectors, and you can take alpha, beta, gamma. You can write gamma to be 1/4 of alpha plus. So they are not independent. Okay. So now let's skip this
So
question.
that option is linearly dependent.
That was for linearly dependent. She asked a different question. Okay, now let's come to the basis. So a set of vectors in vector space that span the whole vector space. Okay. That means the vectors S is the spanning set of V. Okay. This also you can say that S is the spanning set of V. If you call this subset of V's. And the second condition is that all these vectors are linearly independent to each other. That means if you express linear combination of these vectors for 0, then all the coefficient must be 0. For an example, you can take the canonical basis in R3. They are always they form the basis. But if you look at the second example, they are not the basis. So how to check they are not basis? So you can check because there are three vectors. So that is sufficient condition for spanning. Okay, they can at least span, but independency we need to check. So you can check the independency by taking the writing them in the column, or you can just simply see that the first vector can be obtained by linear combination of the last two vectors. So they are not independent. Okay. Now let's look at this question. Which of the following is true? Any minimal spanning set of vector space must be basis. True or false?
True, sir.
True, sir.
True.
Yes, this is one of the equivalent definition of basis. So this is true. Any maximal spanning set of vector space must be basis. It's false.
False.
Because there is no limit to the spanning set, maximality of the spanning set. It can have infinitely many. It can have 1,000 vectors also. That may also span the vector space. So there is no limit to maximum. Any minimal linear independent set of vectors must be basis.
False.
Oh, sorry, maximal linear. A singleton vector is also independent, but it doesn't form the basis of R3. Let's think of it in this way. So this is false. Maximally independent vectors, yes, it does form basis. Basis of a vector space is unique.
False.
False.
Yes, there can be infinitely many bases. The number of elements in basis of R3 is 3.
True.
Right. Number of elements in basis M 3 cross 3 is 3.
False.
What's the dimension? What is the number of bases?
9.
9.
9.
So there are infinite number of bases of R3.
True.
True.
Any subset of minimal spanning set B cannot be a spanning set.
True.
Because it's the minimal span. So if you take
Yes,
if you
yes.
remove one of the vector, then it will no more span.
It will no more be a spanning set. Yes.
Because if it was a spanning set, then it will contradict the condition, contradict the hypothesis that you started with a minimal. Correct? So this is false. Okay, Amol, what is your doubt?
Sir, the basis of the vector space is unique. So could you explain a bit more about this? So unique means
Unique means one, single, but that's not the case. So for example, this is one basis. Well, let's take R2. So this is one basis, 1 0, 0.
okay.
Is that the only basis? No.
No.
Yeah. You can take, what are the other choices? You can take 2, 0, 0, 2 also. You can take 3, 0, 0, 3 also. All of them are bases.
Yes, sir. Okay.
So there are infinitely many choices.
Okay. I got it.
Yes. So Margia Mukherjee.
Yes, sir. For that part, that 9, sir, how that 9 came? That number of elements in a basis of M 3 cross 3 is.
Yes. So because you can think of as a 3 cross 3 matrix. So you write down all the entries, right? How many entries will be there?
9.
9 entries, right? Now what you do, you think of each entry as variable. So you can do what? You can write it like this, because there are n possible. There are n places where the variable can these n entries can change. These n entries can vary. So that's why the 9 number.
Okay.
And how do you obtain basis? You can just take each entry out and then write it as the sum. So A11 plus A12 0 1 0 like this, and then you will get the basis. Okay.
Got it.
Yeah.
That means
Arnav,
for any-
what's your doubt? Yeah.
Sir, the last option is true or false? I think it was true.
It's
maybe.
false, right? It's false.
But it said that it's minimal spanning. So
yeah.
So if we take a subset, then it won't be spanning anymore, right?
Oh, sorry. It is true. Oh, okay. Oh, right. I misread. Right. It's true. Yeah.
So can you explain the last option again?
Yeah, if it's the minimal spanning set, right? What is the minimal spanning? That it is the spanning set, and any subset of this is not a spanning set of the vector space. Because if it does, any subset of this minimal spanning, if it also a spanning set of the vector space, that means the earlier one was not the minimal spanning, right? Because you have lesser number of vectors that span the whole vector, so it is not the minimal one, but that will be the contradiction to the hypothesis you start.
Okay.
So yeah, this is true. It's not the false. All right. Now let's look at this question. Let V be the vector space defined as follow. Then which of the following forms the basis of V? Okay. So how to solve this question? So you have given an equation x plus z equal to y plus w. Right. Now what we can do? We can express one variable one coordinate x in terms of the rest of the variables. Okay, rest of the coordinates. So you can write x as minus z, right? And then you replace this presentation back into the vectors description. So then this will become what? This will become like this, right? And now you can separate. Now you can write it as the sum of how many vectors? 3 vectors. Okay. So y 1 1 0 0. So you can write this vector as y 0 0 plus w 0 0 w plus minus z 0 z 0. Right? And now you can take each one out. Right? So you get the basis.
So can you please explain how you got the second step? This y comma 0 comma 0.
Yeah. This to this.
Yes, sir.
Okay. So you think of it as okay. So discuss another way in our lectures of the school. So now what you do, you want to find out the basis. Okay. So what you do, you first take y to be 1, z to be 0, w to be 0. Okay. So what will you get? 1 1 0 0. Now you take y to be 0, z to be 1, w to be 0. What will you get? What will be the answer?
-1.
That's all?
No. There is no. -1 0.
-1 comma 0.
Right? If you take now, what's the third possibility?
W will be 1.
And other will be 0.
0.
Right? So what will be the vector? 1 0
0 0 1.
0 1.
Right? So this is how you can get the basis. So first you need to write down the general form. Okay, from using the equation. So this was equation given. You can express one vector in terms of the other. Suppose if there were two equations, so you can express x in terms of the variable, and then you can also express another vector with respect to the other variables. Okay, so you can do that, and once you do that, now you express your general vector like this, and then you try to separate, and then you use this notion. Put y equal to 1, other to be 0, y equal to 0, other to be 1. You will get this. Okay. Yes, Anna?
So this is the method that we would follow for every type of question, right?
Of this type of question.
Of this type of question. Okay, sir.
Yeah, where the equations are given.
Okay.
Yes,
now,
sir.
what is the correct answer?
Yes, sir. Actually, my doubt was regarding the matrix form. Actually, if we were given a matrix form, then how would we do it?
Matrix form?
Like for this equations, for some matrix 2 by 2 or something 3 by 3, then.
Can you be more explicit about what you are saying?
Like we are given a condition like a matrix of a upper triangular matrix is given for a vector space V, and we have to find the dimension or something like this, same form a basis of V.
This for that, I think you can draw the matrix and then find the number of free variables.
Yeah. So, are you asking this that you have 2 cross 2 matrix such that something it satisfies some equation?
Yeah. So for some condition like
Something
A
like
is a
this.
upper triangular matrix.
Oh, okay. I will come to that.
Okay.
So what is the dimension of vector space? Now the cardinality of basis is called the dimension of vector space. All right. Now how to find out a vector space, which is a find out the basis of a vector space, vector subspace of Rn. Okay. So what does this mean? That you have given set of vectors V1 to Vn in Rn, and then you want to find out the basis from that. So how do you get? So you will first write down the basis. You first write down the, suppose you have given vectors like this. Okay. So now these are vectors, these are 4 vectors in R4. So now what is the first? My first point is to, and you want to find out the basis of the span. Right? You want to find out the basis of their span. So let's call that S, and then you want to find out span basis of the span. All right. So now each form a matrix A with each of the vector as a row. All right. So now you write down each of the vector as row. Okay. Then you perform row operations. Okay. So let's perform row operations, and then you will obtain something. So R3, R2 minus 3R1, R3 minus 2R1, and R4 minus 2R1. We get 1, 3, 4, 2, last row. Second row, 0, 4 minus 9 minus 5, 5 minus 12 minus 7, minus 6 minus 5, 0, 6, 2 minus 6 is 4, 3 minus 8 minus 5, 4 minus 8 minus 5. Right. And then you can further perform row operation, then you can at the end obtain the RRE, not doing the complete calculation. And then now you look at the third option, the non-zero rows of the RREF or REF forms a basis of the span S of the vectors. Okay, so you look at all the non-zero rows, that will be your span of the basis. And then what will be dimension? Dimension will be precisely the number of non-zero rows. Okay, so that will also be called to be the rank of this matrix. That the matrix that you using the rows, writing vector as rows. All right, now let's look at this question also. This question in it, you want to find out the dimension of the vector space given like this. So again, we have 2 equations. X plus y equal to z plus w, and x plus w is equal to y plus z. All right. So what I will do first, I will express x in terms of y, z. So you can simplify this equation. You can write down these equations as x plus y minus z minus w equal to 0, x plus w minus y minus z equal to w. Or more precisely, you can write down them accordingly. Okay. Now you can see that this is nothing but a homogeneous system of equation, and the solution of that will be the vector space. So let's not go into that because it is not part of your syllabus, but you already know this is an analysis of this system. But let's not go into that. So how to find out the equation? How to find out the vector space or dimension of this? So you just form the vector. You just form the basis corresponding to it. So you will get 1, 1, minus 1, minus 1, 1, minus 1, minus 1, minus 1, 1. All right. And then x, y, z, w will be here, and then we will have 0, 0, 1. So just look at the coefficient matrix. Now you perform row operation. So and obtain the RRA form. So R2 minus R1. All right. Now you divide R2 by 2. R2 by minus 2. You get 1 and then minus 1. Right. So this is what you have obtained. Now let's translate it back into the homogeneous system. So what is this? It is x plus y minus z minus w equal to 0. Y minus w equal to 0. So now you can simply write. Okay, now let's further do one more thing. Let's obtain the RRAF form. So R1 minus R2. So you will get. So what you will get? You will get 1, 0, minus 1, minus 1 plus 1. So you will get 0, 0, 1, 0, minus 1. All right. Now you convert this into homogeneous system equation by multiplying x by z double. X minus z equal to 0, y minus w equal to 0. Now this will tell you that x is equal to z, y is equal to w. Now you use this relation in your vector space definition. So your vector subspace will be, so your general vector x, y, z, w is going to look like x. Now x is z and y is w. Again you have z and w. So now there are two variables. All right. So you have reduced your vector space has only 2 variables. So what will be dimension? Now you can find out basis also. First you take z equal to 0, z equal to 1, w equal to 0. You will get so first you do z equal to 1, w equal to 0. You will get 1, 0, 1, 0. And when you put z equal to 0, w equal to 1, you will get 0, 1, 0, 1. All right. So how many bases are there? 2 bases. So what will be dimension?
2, sir.
All right. Got it? There is nothing difficult about it. Okay. So this was the question that one of you were asking. So let's do this. So V1 is a set of all 2 cross 2 matrix where A is symmetric. This, and we need to find out the dimension in each of the cases, right? So let's do one of the questions. So which one you want me to do? Which one you guys think it's difficult for you to solve? At that I will do. Others I will just skip. So let's do the symmetric one. I think that's what. Yeah. So what is a symmetric matrix? Symmetric matrix is A transpose equal to 1. So let's write the general form of the matrix ABCD, and then it should be equal to the transpose. So what is the transpose of ABCD? It is A, C, B, D.
C.
Now, right now you do 1 by 1. Okay, coordinate wise you equal. So A is already equal to A, B is equal to C. So B should be equal to C, and C should be equal to B. That's the only relation we get, that B should be equal to C. So now, what will be your general form of the matrix in B1? It will be A, C, C, D. Right? So how many variables are there? There are only 3 entries. Okay. So what will be the dimension? V1 dimension is, so A is
3.
Right? Yes. For a scalar matrix, what is a scalar matrix?
It will be 2, sir.
Yeah. What's the definition of scalar matrix?
What's the definition? Means only the diagonal element would be there and it would be same.
Yes. It's a diagonal matrix with both of the diagonal entries to be same. Right. So you have, so on all the other entries are 0. So you have A, and 0, 0. That's the scalar matrix. So how many variables are?
2.
No, so one.
1.
One.
There is only one variable, right, which is A. So what should be the dimension?
One.
So this option is wrong. That's correct. Similarly, you can figure out all the other options. Okay, I'm not doing one by one. You can do the same thing.
So just the last one, all VIs are subspaces. So what we have to do in here?
No, there's no question about this. They are subspaces.
Okay. Sorry, sir. Okay, sir.
Yeah. Okay. So now rank of the
So
matrix.
can you explain it again?
Which one?
The previous question, dimension.
Which part of it?
Like how you said dimension is 1 for it. I didn't get it. We have to just check the
So what
number
is the scalar
variable.
matrix? Yeah. What is the scalar matrix? Definition of scalar matrix.
Diagonals will be same.
Diagonal entry will be same. And it's a diagonal matrix.
Will be 0.
Right?
So your audio is breaking.
Is it breaking for everyone?
So now it is clear. Now it's clear.
Now it's clear.
Yes for breaking or yes for not breaking?
Now it is not breaking. It is clear now. First it was breaking.
Okay. So scalar matrix. What is scalar matrix? It's a diagonal matrix with the diagonal entries same. Okay. So then there are two diagonal entries, right? Off diagonal entries are 0 and diagonal entries are same. That means AA, right? So now this is the general form of this matrix. Okay, any matrix is going to look like this. Now what you can do, you can again express this. You can take A equal to 1, and because there is no other variable, so you don't need to take anything else. So what will be the basis? Basis will be 1, 0, 0. Now how many bases are there? 1. There is only how many elements in the basis? 1 element in the basis. So dimension is 1. Make sense?
Okay. Yeah.
So, I have a query. So, what if in one V1 case there is a symmetric? So, what if we have a skew symmetric matrix in the instead of symmetric matrix?
Okay, let's do skew symmetry. So, what's the definition of skew symmetry?
So, A, B, then negatives.
It should be equal to negative of the transpose.
Negatives of the transpose. Yes, sir.
So that means minus A, minus C, minus B, minus D, right?
Yes, sir. Yes, sir.
Okay. So now, but these two matrices are equal. So this forces us that A equal to minus A. All right.
Okay.
Which means that 2A is equal to 0. Which means A is equal to 0. Similarly, B is equal to minus C. And C is equal to minus B, which is the same condition.
Yes,
Third
sir.
condition is D is equal to minus 2. So this also forces us to D equal to 0.
So the dimension is 4.
Just wait. Now write down the general form of the matrix.
Yes.
So A is 0. What is B? B is B. What is C? C is minus B. What is D? D is 0. Now what's the dimension? Now there is only one variable B. So take B equal to 1. Then what will be basis? Basis will be 0, 1, minus 1, 0. How many elements in the basis? 1. So dimension is.
Sir, I didn't get how many elements in the basis. What you meant by that?
So what is the dimension? Dimension is cardinality of basis.
Cardinality of basis.
So when I say elements, number of elements in the basis. When I say how many elements in the basis, that is number of elements, number of vectors in basis.
So, but here it's 2, right? It's 0,
Yeah,
minus 1 and 1, 0, right? There are 2 elements, like 2 vectors. It's like a negative value here, right?
No. This is matrix. We are working with matrix. So matrix become a single vector.
The whole matrix is a single vector.
Yes. It is not your usual vector space Rn. It is not a subspace of Rn. It is not Rn.
Okay.
So, sir, the case in every matrix it would be 1, is it?
Sir, your voice is breaking again.
Yes, sir. Still now it's breaking.
Am I audible?
Yes, sir. Now it's okay.
Now it's
Yes, sir. Now it's okay.
Okay. Okay. Okay. Is it clear to everyone?
Yes,
I didn't
There are
get
no
clear
two
what you
bases.
said.
Our vectors
Yes,
are
sir.
matrices in this case. What is a vector space? Vector space is 2 cross M2 cross 2. This is your vector space. So each element in your vector space become the vector. Now, what are the elements? Matrices are the element. 2 cross 2 matrices are the element. So your vector in this case is the matrix itself. Okay. So when I say basis, so basis will also be formed by some number of vectors or some number of matrices. Okay. So we just need to count those.
Yes.
Yes, Ajit.
Sir, I have a doubt in general. Like, we have triangular matrices, right? When we
Yes.
like perform an intersection between upper triangular matrices and lower triangular matrices, will it give us an empty set or the diagonal matrix set?
Okay. What do you think?
Like, because see, I looked up the definition for triangular matrices. It said that either the lower half should be 0 or the upper half should be 0, which makes it a diagonal matrix. I mean, the triangular matrix. For diagonal matrix, only the diagonal elements are,
Diagonal yes.
and the other
So
elements zero.
yeah, so you are correct. You are correct. So the intersection of upper triangular matrices and lower triangular matrices will be such the diagonal matrix, because diagonal entry is also upper triangular matrix and it is also a lower triangular matrix.
Okay, so it will be it will be the diagonal matrix set, right?
Yes. Yes.
Okay. Thank you.
So for the previous question, we had like those two equations, right? Can we like since like we actually substitute the values of x and y here, right? So we can just say
Yes,
that
yes.
since x and y is written as a combination of the other elements here, which is z and w, we can say
Yes.
both of them are dependent and rule out and then just say that the dimension is just
Yes.
2.
Right. Right.
Instead of doing every all of this, I can just actually look at the question and then okay, fine, x is equal to something and y is equal to something, and I can come to a conclusion that the dimension is just 2. Can I do that?
But what may happen is that there might be then 2 equations or 3 equations, but some of the equations are same. It may also happen. Right.
Oh.
Right.
Oh.
So, for example, if I say, let's say, x plus y is equal to z plus w, and then I also write a similar equation like 2x plus 2y is equal to something like 2z plus 2w. So they are same equations, but if you just count the number of equations, then that will be a problem.
Okay, so this is like
But just make sure
values. Okay.
Yeah.
Okay, sir.
But your intuition is correct that there are 2 dependent variables and others are independent variables. That is correct. Okay. So now let's recall what is the rank of a matrix. So we have already seen the rank while doing this exercise, right? You perform the RREF form and the number of given a matrix, you perform the row operations, you obtain the RREF form of that matrix, and the number of non-zero rows in the RREF is called the rank of the matrix. All right. So so you know what is what are the column. Yeah. So we know what are the column space is the span of the columns of a matrix. row space is the span of the rows. Column rank is the dimension of the column space, and row rank is the dimension of the row space. Right. So, but column rank and row rank are all same for any matrix. They are both same thing. So we can define rank of the matrix as the row rank of a matrix or column rank of a matrix. Both are same. It doesn't matter. Now, how do we calculate a rank? So to calculate a rank, we need to first perform the row operation. We obtain the RREF form of the matrix, and the number of non-zero rows in the RREF is called the rank of the matrix. All right. So now let's do this question. If the rank of this matrix is 2, then find the value of 2. So there are 2 ways to solve this. So I want to expect at least one way from you guys to tell me which one you will do.
Sir, either we can find the determinant, it should be equal to 0, or we can use the RREF form, the last row should be 0.
Yes, good. But why determinant?
So if the last row is 0, then obviously determinant will be 0.
Right. In the RREF. Right. So let's do the determinant one. Or let's do the RREF. Okay. So let's convert this, because the rank is not the full rank matrix. So we must be able to obtain a zero row in the RREF form. Okay. So that means the determinant must be, so if the RREF form has zero row, that means the determinant of the original matrix is also 0. That is what we have. I have also said once in one of the lecture. So because we can backtrace the determinant. So if the RREF form has any 0 row, then the determinant of the original matrix must be 0. So we can use that. And that is clear because the rank is 2. So there must be some 0 row in the RREF. So yeah, so we can just directly take the determinant of this and equate it to 0. So can anyone tell me what's the answer?
I think it's 5.
Okay. What about others? Do others also things?
So can you please repeat this? Why you take this determinant value is equals to 0?
Is 5. Yeah. So because the rank is 2, right? What does it mean? What does it mean that rank is 2?
So there are only 2 variables. Like,
Yeah, that's one way to say it. But
and the third row would be 0.
Yes. The RREF form, the correct statement would be the RREF form of the matrix. It has third row equal to the third row is 0 in the RREF. Right? There are only 2 non-zeros. Right? So now you recall one of the lecture that when you can use RREF form to obtain the determinant. Okay, you can backtrace your every every row operation. You can obtain the matrix. You can obtain the determinant of the matrix, original matrix. Okay, so if the original yeah, so if the determinant is 0, if the RREF form is nullity is 2, that means one of the row is 0. Okay, so rank is 2. Rank of A is 2. That means RREF has a 0 row. That means rows. Think of row as vector. The rows are dependent. Right? Rows are dependent, linearly dependent. Linearly dependent. Right? That means what? That means the determinant of matrix should be
0.
Right? So
Okay.
you can follow this.
Thank you, sir. Now it's clear.
Series of. Okay. Now let's do this question. Now in this question you cannot apply determinant. Why? Because it's a 3x2 matrix. Determinant does not make sense. Now how do you solve this question?
So by reducing it to RREF form.
Yes. So let's do that. So 3, 1, 3, 4, 2, K1. So now what's the first operation?
R2 is equals to 4R1 minus R2.
So R2 minus 4R. Second operation is, okay, so let's do that. 1, 3, 0, 2 minus 12, minus 10. Right? Third row remains as it is. Now, what is the next operation?
R3 minus KR1.
R3 minus KR1. Right. 1, 3, 0 minus 10. 0, 1 minus 3, 2. Right? Okay. So now, then what?
So K must be 1 by 3.
1 minus 3K equals to 0.
The rank is 2, so the last row should be 0.
1 minus 3K equals to 0.
So minus 1 by 3. 1 by 3.
Right. Is that the only possibility?
Yes, sir. K is 1 by 3 also.
Yes, sir.
What about
A can be 0 also.
K is 0? K can be 0 also.
Yeah.
Yes,
So
that is also one of the possibilities.
Yeah.
What are the other possibilities? Then K 1 minus 3K is equal to 0. That is the other possibility. That means
K
K
can't be 0.
1
If
by
K is 0, then it comes 1.
Sir, but K is 0, then 1 is not equal to 0, na? Then how?
then it was not in RREF form. Right? So you still need to perform some step to get RREF. Right? That means what you do R2 by minus 10. 1, 3, 0, 1. 0, 1 minus 3. Right? Now, what will you do? You can now you can subtract. So now what are the possibilities? That 1 minus 3K is 0. That's something. Then it will be in REF form. That's the first possibility. Second possibility is that second possibility is that 1 is equal to 1 by 3, 1 minus 3. Right?
Yes. Yes.
Yeah.
Yeah, 1 is equal to 1 minus 3. Right? So let's explore that. So this will imply K to be 0.
Sir, we can perform the row operation R3 minus 1 minus 3K into R2.
Yes.
To reduce it to RRF form.
Okay, so let's do that. R3 minus 2R.
Not 2. So
R3
1 minus 3.
minus 1 minus 3K into
R2.
R2. Yeah. 1, 3, 0, 1. Yeah, but it doesn't give you any information about K.
But sir, it is reducing to RREF form now. Finally.
It is reducing to RREF form, that is true. But
That means K can be any value. K can take any value.
Yes. Yes. K can be any value.
Sir, here C should be 0, no?
No, what he's saying actually correct. K can be anything. It doesn't matter what K is.
No, sir, 3, that second column.
Yeah, you can remove this. There's no problem. R1 minus 3 R2. Then it is this. So here K can be anything. That is correct, because you can always remove that, and you can still get you can still get the RREF. So K can be anything. There is no condition on K that we are getting. So K can be anything. So it does not matter what case. But you understand, if such type of question comes, then you know how to solve it. You can perform the row operation, then you can find out, use that row operation. That will give you some relations, and that relation will help you to find out the value of it. All right, like we did in this case. But in this case, you can also use determinant matrix. But if the matrix was not in 3 cross 3 form, it was, suppose it was in 2 cross 3 form, or something like this, then you have to apply. You cannot apply random. Okay.
So if there are many solutions, what would it like here? I mean, this type.
Yeah,
of
in this case, you, this type of question will not come, because there is no one solution. Right?
So in this
you will only
question,
get questions which has.
sir, please, in this question, the rank is given as 2. Is there any importance for it? So here rank is 2 means only that implies 1 minus 3k should be 0.
No. That's not the only solution. That's what we figured out, right? There can be any solution. K can be 0 also. K can be 1 also. K can be anything, because
But sir,
the first two rows.
Excuse me, sir. So rank of a m into n matrix is maximum rank can be min of m or n.
Yes.
So it will be min of 3, 2. That is 2.
Yes.
That can be maximum rank.
Yes.
so it does not matter whatever is inside the rectangular matrix, right? Does it?
In this case, it does not matter. Now let me give you another example. Okay, so that, because this question is not. Okay, now let's do this question. Okay, this has rank 2. Then what is K? All right. What about this question? Let's solve this. So we can clearly see that the second row is the multiple of the first row. So we can just directly remove that. We will get 1, 2, 0, 0, K1. Right? Now let's R3 minus K R1. What we'll get? 1, 2, 0, 0, 0, 1 minus 2K.
2k.
Right? Now further, yeah, now because this has rank 2, so second row must be non-zero. Right?
So K is half.
So we should equate it to this, we should equate this thing to 1.
1.
Right? Which will imply that K is 0. Right? So this should be, so second row must be non-zero. That means 1 minus 2K should be equal to 1, which will imply that K will be equal to 0.
Excuse me, sir, we can divide by 1 minus 2k the third row.
Yes, sir.
So how
If it
rank
is
is
not zero.
one?
If it is not zero.
Rank is
Can you repeat that?
So we can divide the third row by 1 minus 2k. 1 minus 2k is not 0.
Yes.
So in that case, again, k can be any value.
Yeah, other than half. That is true. Right. So this is also not a good question. So let's take rank to be 1.
So in this
Now,
question, k can be any value other than one, other than half.
other than half. Yeah, that is good. Now I've changed the question. So I'm improvising. So now let's you have a matrix has rank 1. Then what is k? Now you can have definite values. Right. So
1 by 2.
So it should be 1 by minus 2. 1 minus 2k should be 0. This will imply that k has to be 1 by. Right. Thanks. Thank you guys for being attentive. So it gives it makes sense now. Okay, so it has to be 1 by 2. And then yeah, so you will get rank 1. So it will force you to have up. So you can get so this kind of question which makes sense. Okay, so my questions were not making sense because you were getting infinitely many values. Right.
So why did you equate this to 0? Like 1 minus 2k is equal to 0?
Because
Yeah,
the rank is
because
1.
Oh, okay, okay. The
because
rank
the
is
rank
1
is
now.
1.
Okay, okay. Okay,
Yeah,
okay, sir.
I updated the question.
Okay, sir. Okay, sir.
Yeah. All right. So my earlier question could have been find the value where the rank is not equal, where the rank is not 2. Find the value of k where the rank is not 2. But okay, it still makes sense. So you get the idea. All right.
So, sir, if your question
yeah,
was with rank 2 and what value of k cannot take, that would make sense, wouldn't it?
yeah, that
Because
would make
we
sense.
need
So
two
then again the
variables.
answer will be right. Yes. Then there is another way to think of that because it is just yeah, because it is ranked 1. So all of them has to be multiple of 1 comma 2, the first four. Right. So in that way you can just simply write 1 comma k comma 1 to be this multiple of some multiple of 1 comma 2, which will force you that a should be half, and then it will force that k should be half. That is also another way to solve it. But okay. You can also do the row operations and you can obtain the row echelon form, which is the standard one. This may not work always, but okay. All right. I hope this today's discussion was helpful. And yes, Somalia Day, you have anything to add?
Sir, I came across a question which said that the rank is at most 2 or at most 3. Then how to solve those questions?
At most 2, at most 3. Okay. Can you give me the question?
The question was similar to what you solved. I mean, a matrix was given, and one of the elements of those matrix was an unknown, and we have to find that unknown given that the rank of that matrix is at most 2.
At most 2. Right.
Yes. Then how to solve those questions?
Yeah, you can solve in this way, the same way. So, so at most 2. So then you can say what was the matrix order. It depends on many variables. Suppose if it's 3 cross 3 matrix, let's say, and the rank is next at most 2. That means you can take determinant of that. Then determinant must be equal to 0. So you can get the value of k. Right. If it is, let's say, 3 cross 4 type matrix, then the maximum possible rank is 3. So then one of the row in the row echelon form, you can reduce to the row echelon form because it is at most 2. You can use some relation. So the one of the row will be, then you can find out some of the relation like this to get the value of k. Okay. So it depends on the question, type of the question. But always you can reduce to RREF form and then you can work out things. You will get some relation at the end in terms of your unknown.
Okay. Yeah, this question was given in one of the PAs, and I saw the solution. In the solution, it was given that they used something called as nullity.
Nullity is not part of this
Okay.
question.
Okay.
It is part of the next one. Yes, people.
Sir, I think in above pages you had to skip one question which mentioned something y equal to mx. If you could
Right.
that.
This one, right? Okay, so what does this question say? This question says that V is a vector space, y is equal to mx, where m is not 0, x, y, m is r in R. The usual addition is scalar multiplication as R2. All right. W is another subspace usual addition as this. All right. Choose the correct option. 1 comma m, 1 over m comma 1 is a linear independent set in V. So what is first of all V? V is nothing but whole R2. Okay, because it is set of all lines that passes through origin. Right. So it covers all the points of R2. Okay. So V is nothing but R2. Now the set of vectors 1 comma m and 1 by m comma 1 is linear independent set in V.
I think false. They are dependent.
They are dependent. Yes, you can just multiply m.
1 by m in both.
Determinative A will be 0.
Yes.
Determinant equal to 0.
So you will get this, and determinant also you can say. Now the set 1 comma m and 1 over n is a spanning set of V.
True, sir.
Yes, true.
Huh?
It is
Is
true.
it a spanning set?
Yeah.
Yes.
Yes, sir.
No, but they are dependent. And if the space is over R2, then how can this span?
So it is asking only about spanning set, right?
Just a second. So it is x comma mx. Right. But m is also there. That's the point. M is also there. Right. So if you have two vectors, x1, mx1 plus, let's say m1 x1, and then x1 m2 x1. Or yeah, let's take this. So then what will be their sum? Their sum will be x2 x, and it will be m1 m2 x1. So it is not even a vector space. This V is not even a vector.
Why, sir?
Yeah, because look at this definition. So by the definition, it should be their addition should be what? Their addition should be
In the form
yeah.
y equals to
So
mx.
their addition is this. The addition is defined like this, but this is not in V. This is not in V. Why? Because what is the standard form of V? It should be x1. It should be x times mx, right? But I have two x1 over here, and here I have some m, but only x. Oh, I can just. Oh, okay, great. Yeah, I can take it to be 2 there and then multiple of this. So it makes sense. So, yeah, it is in V. That is clear. addition is well defined. All right. What about scalar multiplication? Is more different. So CX and CX. That makes sense. Just take it. And additional different. Multiplication is different. First one, it's also doesn't use that. Additive involves X plus 0 big 0 0 X that is true. That will be there. If you have to work it. This was that is also there. At same time, you can also put minus n x. But this is not there. Yes. That is easy. Okay, this is a vector space. That is clear. Now the set is a linearly independent set. That is not independent.
I think so they can be spanning, but not basis.
Sir, base is 1 comma m, I think, because everything can be obtained from that.
1 comma m is the basis.
Yes, sir.
That is what it is. Or 1 comma m is also said.
Option C.
But the point is, B is whole art, so there must be 2 bases.
Then sir, both the bases can form a spanning set, right?
Just a second. Just give me.
Basis should have 2 elements in this because it's R2.
Yes, that's what I'm saying.
Can't be 1.
So if this, yeah, so if they are a spanning set of B, that means it is a minimal spanning set. So that means they need to be independent, but they are not independent. So these 2 conditions, they cannot be true at the same time. That's what I'm saying. Because V is nothing but R2. Okay, you can have any point. Yeah, you can have any point. Let's say 3 comma 2, or let's say A comma B. Let me write A comma B. You can think of A comma B as A, and then B by A. All right, this B by A will be your R. If A is non-zero, obviously, if A is non-zero, and if A is 0, then you can think of it as okay. If you have 0, then you cannot write. Then why? Yeah, if A is 0.
B will also be 0.
Yeah, but
Sir, actually, sir, it doesn't span the whole R2, I think, because it doesn't span the
yes, it is not spanning the whole R2. Yeah,
the y-axis.
This basically 0 comma 1. This 0 comma 1 is what is remaining. Yeah, when x is equal to 0, that is actually the W subspace. 0 comma 1. When you have 0 comma 1, the span of this is not part of this V. So it is not polar. Okay. Okay, that is clear now for me. Okay. Sorry guys, I've taken so much time of yours. But I just wanted to make sure that I understand this. Okay, so it is not part of R2. So it is not R2. It is not R2. That is what confusing. It's not R2. All right. It is basically R2 minus W. Where the W is the next thing that happens. So it is R2 minus W. Okay, so they are independent set. That is, they are independent. Okay, so now it makes sense. They are dependent. So are linearly independent set in V? No, that is false. Are they spanning set of V? Let's check that.
Yes, sir.
Okay.
So
So
in
now,
spanning set, does it have to be the elements are dependent or independent, something like that?
no. Spanning set can have dependent elements. It doesn't matter. Because in this case, they are dependent. Right? So, but the question is, do they span all of the space? I don't think so. They span. So what about if I take? So it is what? It is 1m. So if you take a multiple, so it will be this am. But if I take a different value of m, let's say m2, 1 comma m, then it does not. 1 comma m2 cannot be written as a comma 1m, right? Because if it does, then it will be am. So it will force a to be 1 and m to be m2, which is not the case because I started it for m2 not equal to m. Okay, for m2 not equal to m. Yeah, this forces m to be equal to m2 upon condition. All right, so this is not a spanning set also. That is clear. Now 1 comma m is a linearly independent set in V. Yeah, singleton is always a linearly independent.
Yes.
That is true. 1 comma m, so that is also. Singleton is always a linear. All right. So this is also over. Okay. Thank you guys for joining. I hope I made sense whatever I said today. And all the
Excuse me,
best
sir.
for-
Sir,
Yeah.
just one doubt, sir. Could you please go to practice assignment 4, question 5, sir?
Practice assignment. Question 5. All right.
Yes.
Yeah. So at most 2, right? It's a 3x3 matrix, and it is asked that it is almost 2. So let me do one share.
So, like, how do we solve that those kind of questions?
Yeah, you just take the determinant of this. Determinant will be 0 because it is at most 2. So that means it is not a full rank matrix. So if you perform the RREF form, you will get a 0 row. I just explained this. You can just go through the slides recording of my session. So then the determinant of this matrix will be 0. So just compute the determinant. Okay. So if you compute the determinant, you will get a, I think, quadratic equation. Yes, you will get a quadratic equation, and you will not get a quadratic equation. Let me see. Yeah, you will not get a quadratic equation. You will just get a linear equation, and then you solve m in that. That's so simple.
Sir, so basically those columns are treated as like say,
No, do not treat
elements
anything
of a
as something.
basis.
You just take the matrix. You just use the determinant of this to equate to 0.
Okay, fine. Yes. Thank you, sir.
Yes, Sakshi.
Sir, can you please explain the rules, all the rules for rank related, whatever the rules are, like less
You can
than
go
or
through. You can
greater
go
than
through the
all the
live session.
formulas?
You can go through the live session videos, and it is all there. I don't want to repeat all those things.
Sir, can you please tell particular live session, because I have attended almost all the live session,
Rank
but
is this is
still.
a live session. You can go to the recordings. Whatever is there in the recordings, you can just go through once, run it at twice the speed. You can go through the notes. You don't need to go through the live session. You can just go through the notes. It's all. Yes, sir.
Okay, sir.
Yes, sir. Regarding the question that you solve, where the condition was given like x plus z equal to y plus w.
Right.
Yeah. So, in that regard, can we a type of question can be made like where x, y, and z, w are given in a matrix form, and the condition is same.
Yeah, you can have anything like.
But the approach will be the same, right, to solve it.
I don't understand what do you mean by matrix.
Like where x, y, z, w is given as a one vector in the question, so can we make it into a matrix for like x, y is in
If
one
it is
row
given
and
a vector, if it is a given a vector, then it's a different scenario. Then you can write, you can form a matrix by treating each of the vector as row of that matrix, and then you can find out the row space after reducing it to RRA form and all these things. Then you can find out the basis for that.
okay. But like a matrix like x, y is in one row and z, w in another row, and the condition is same.
Then you can write down your xy again in terms of zw using the relation given, right? And then you can
Okay.
solve this.
Okay.
Yes, Somar. Somar, you have anything?
Yes, sir. Yes, sir. Then the last question, that y is equal to mx. Sir, how come the first option that 1 comma m and 1 by m comma 1 is linearly independent, it's wrong?
Okay. If you multiply 1 over m to the first vector, you will get the second vector.
Yes, sir.
So they are dependent, right?
Oh, yes, yes, yes. And for the second, as I said, 1 comma n and 1 comma n, spanning set for v.
Yeah, the proof is over there. You just see the screen. If you take something other m2, which is not equal to m, then that 1 comma m2 cannot be expressed as the linear combination of this thing. Linear combination of the ones. Okay. Because both vectors are dependent, so you can just take one of the vector and you can, if they have to be spanning set, then they have to be multiple of this 1 comma m2 has to be multiple of 1 comma, and then which is not true, which forces you that m should be equal to m2, which is not the case, because I started with something which is different from.
Okay, sir. Got it.
All right. Thank you all for joining. We stop today's session now.
Yes, sir.
And all the best for the quiz.
So one last thought. So what are the portions